Hello everyone, this is Group 4 and our topic is Bigtable, a distributed storage system for structured data. In our group, there are 3 members. I'm responsible for introduction and data model design of Bigtable, and Zhang Yuyi will illustrate part of implementation and applications. In the last session, Zhang Jing takes charge of the refinement of Bigtable and evaluating the system performance. First of all, Bigtable is a distributed storage system for managing structured data, which is built on GFS, Chubby, SSTable, and other Google technologies. It has achieved many goals, including wide applicability, scalability, high performance, and high availability. For example, more than 60 Google projects use Bigtable to store data, such as Google Analytics, Google Earth, and personalized search, etc. And Bigtable can meet these products' changing requirements and successfully provide flexible and high-performance storage solutions. Secondly, Bigtable resembles a database and uses many database implementation strategies. However, Bigtable does not support a full relational data model. Instead, it provides a simple data model for the client that can dynamically control the layout and format of the data. In terms of data model, essentially, Bigtable is a key-value mapping, which is sparse, distributed, persistent, and multi-dimensional sorting. It has 3-dimensional keys, which are row keys, column keys, and timestamps. Figure 1 represents a key-value paired record. The first level of the table index is row key. It can be any string of bytes. Reading or writing is atomic. Bigtable stores data in the lexicographic order of the row keys. In Bigtable, table is automatically divided into tablet based on row keys, and the tablet is a low-balanced unit. The initial table has only one tablet, but as the table continues to increase, the tablet will automatically split. If we see the column, time, and value of the row as a whole, it can be reduced to one-dimensional key-value mapping, like shown in Figure 2. Columns are second-level index, and the columns owned by each row are unrestricted and can be increased or decreased at any time. For the sake of management, columns are divided into column family that store the same type of data, and its named format is family colon qualifier. In this case, the time and value are considered as a whole, and Figure 3 displays 2-dimensional key-value mappings. The timestamp is the third-level index. Bigtable supposed to see multiple versions of the data. The basics for version differentiation is timestamp. The timestamp can be assigned by Bigtable and the client. Different versions of data are stored in descending order, so the most recent version will be read first. In the query, if only the rows and columns are given, the latest version of data is returned. If the row, column, and templates are given, the data whose time is less than or equal to the timestamp will be returned. In this paper, the author designed on this data model for keeping a copy of a large collection of web pages and related information, which named Web Table. Feature 4 is a slice of an example table that stores web pages. In Web Table, each row stores a web page, and its reversed URL is used as a row key. The reason for the reversal is to allow the pages in the same domain are grouped together. The column family anchor saves the reference side of the web page, and another column family contents stores content of the web page. In Web Table, the author only keeps the most recent 3 versions of every page. In the part of building blocks, as mentioned before, Bigtable relies on several Google technologies. Google File System is used to store logs and data files. Data is stored in SSTable file format, and Chubby is used to manage metadata. The full name of SS table is sorted string table, which is an unmodifiable and ordered key-value mapping, providing query and traversal functions. Each SS table consists of a series of blocks. When the SS table is accessed, the entire index will be read into memory. Chubby is a highly available distributed log service, which is used for tablet positioning, status monitoring, and access control list storage, etc. It has 5 active replicates. Only one master replicate provides service. It uses Paxson's algorithm to maintain consistency, and its client must maintain a session with Chubby. If the session is expiring, all logs will be lost.
And now I'm going to introduce the implementation of Bigtable. It has 3 major components: a library that is linked into every client, one master service, and many tablet service. The main function of master is assigning tablet to table service, detecting addition or expiration of tablet service, balancing tablet service load, collecting garage file in Google file system, and handling schema changes. It will be explained in details later. In terms of tablet service, it is used to handle a set of tablets read and write request and the sleep table. Before assign tablet, the master needs to get tablet location information. The Bigtable uses a 3-level hierarchy to store them. The first level is a file in Chubby, which has a location of root tablet. The root tablet locates in the second level. However, in order to guarantee the 3-level structure, the root table never split. The third level is other metadata tablet. Then the master needs to assign this tablet into tablet service. Each tablet service will be assigned to one tablet service at a time. So when a tablet service starts, is creating a uniquely named file in a specific Chubby dictionary and acquiring an exclusive lock. However, during the serving process, some problems might lead to the loss of locks. So once the lock lost, the server stops and requires another exclusive lock. If the file in the Chubby dictionary is deleted by the master, the server will kill itself and release its lock so that the master can reassign itself as soon as possible. The tablet serving operation mainly includes update, recover, read, and write. Updates will store or redo record. The recently updates are in Bigtable and older updates are in SS table files. The redo record works during the tablet recovery. It will reconstruct all of the updates since the redo point. In terms of read and write, servers both check for well-formedness and verify sender's permission. The word operation is committed to the commit log and entered into Bigtable, and the write operation will be operated in the merged view of SS table because the Bigtable for they include all updates. During the writing, compaction will be executed in order to change the size of Bigtable and SS table to keep the system in good condition. There are 3 kinds of compactions. First one is minor compaction. It's converted to an SS table and written to Google file system when Bigtable over a threshold. Yeah, then it's just to create a new Bigtable. The second one is merging compaction. Merge a few SS table to a new SS table. The third one is major compaction. It's just rewrite all SS table into exactly one SS table without deleted information and data. Here are some real applications of Bigtable. The first one is Google Analytics. It is a service that helps webmaster analyze traffic pattern at their websites. In Google Analytics, two tables are used to store website information. Table 1 is a row-click table maintains a row of each end user session. The row name is a tuple containing the website name and time at which the session was created. Then the summary table stores predefined summary for each website. Google Earth is another example. The difference is that the first table stores images, but the images are already compressed, so the Bigtable compression is disabled. Another table stores index data, and we know that index requires faster response, so the table contains hundreds of tablet servers and many in-memory column families to guarantee the faster response. Then in personalized search, users' data are stored in Bigtable. It is easy to understand for every time when you're searching something by Google, the first result is the most relevant one. It's also replicated across several Bigtable clusters to reduce latency due to the distance from clients. Personalized search supports sharing between Google products and other websites. Therefore, the storage consumption of Bigtable should be limited.
Next, we are going to talk about the refinement and the evaluation about the performance. The first refinement is locality groups. A Bigtable group clone families, which are typically accessed together, and create separate SS table for each locality group. And by doing this, it makes read more efficient by only reading locality groups rather than all clones families. It also makes it possible to specify parameters to reduce the cost of accessing the disk. And another refinement is compression. Users are able to control compression, decide which locality groups or SS table blocks to compress. And normally, most users, they use two-pass custom compression schema. By doing this, they will increase the read efficiency by short the decompressing time, since a small portion can be read directly without decompressing the whole file. And it also helps to get better compression ratio because locality groups enhance the performance of compression algorithm. And the next one is caching. Bigtable uses two kinds of caching for read performance. The first one is scan cache. It's a high level. It will cache the key-value pairs returned by SS tables. It also it works well for read the same data repeatedly. And the second cache is block cache. It's a lower level cache. Will cache the SS tables blocks. It helps to get the read performance for read data that is close to data that have recently read. The next refinement is Bloom filters. The Bigtable will create Bloom filters for SS tables to answer the questions whether an SS table contains some certain data. By doing this, it can reduce the disk size by reducing the number of the disk seeks required for some read operations. And the next one is commit log implementation, which means for each tablet server, there are only one single commit log to reduce the disk seek. And also, for simplify the recovery process, we'll be sorting commit log. And for each log, there are two threads to avoid latency spikes. The next refinement is to speed up tablet recovery. The Bigtable uses two manual compacting to reduce the amount of unpacked state when do the tablet recovery, and this enable load the tablet to another tablet server without requiring any recovery of log entries. The last refinement is exploiting immutability. The immutable SS table helps to simplify the Bigtable system. For deleting data, the master can use the garbage collecting to remove the deleted data permanently. It also helps to quickly split tablets by just setting the child table to share the SS tables of their parents instead of generating new site for each child. And now let's move to the performance evaluation section. And first of all, let's focus on the single tablet server performance. And from this table, we can see that the random read performs worse because its bottleneck is the label server CPU. And we also see that random read in memory performs much better because there's no need to accessing block from GFS. And for the random write and sequential write, it performs good because we have one single commit log strategy. And for the sequential read, it also performs good because of the block cache. No need to access the disk. And for the scan, it benefits from the ability of the server to return a large number of the value to a single RPC. Next, we are going to see the scaling evaluation. As shown in this graph, we can see the random read in memory increase largely, but it's not linearly because the imbalanced loading in multi-server configuration. And we also can see the worst scaling case occurs in the random read because its bottleneck, the performance of the CPU cannot improve by increase the number of the servers.